Hello, we are here. We've actually made it in the lab number 2. This is me, Mr. Walker.
I'm me, Mr. Morris.
And we have got lots of special guests that we're going to introduce to you as the time goes on. I am looking a little bit dirty and messy. I have been gardening, which, as you know, I like to do on a Wednesday, and it is hot outside. So I'm sure you're all enjoying yourselves. You've got plenty of water. You're indoors. You're ready to watch in the lab and relax after getting back from school. Shall we have a look at some comments? Let's see what is going on. We've got a few people. We've got Marvel Man Games, who is enjoying himself there. Leo Tranter-Perkin, who I can tell you is in the room with us now, and he is watching the comments. We will see him later on. Who else have we got? We've got
lots of good luck messages.
Which is very nice.
Thank you very much for that. Lots of good luck messages. Anyone
there? Yes, there's lots of people here. Yes. Hello. Hi. Henry G. Oh, hello, Henry G. Very nice to see you there. Yes. We have followed Henry G. If you would like to follow him, he would love to have more subscribers. I know that already. What else have we got? We've got, what's this? Interesting.
Oh, interesting. Some of our year 10s watching from the gym.
Good. Well done, lads.
Watching from the gym.
Yes. Get in the gym, which is what I need to do. But I'm not going to. I'm going to stay here.
I might go later.
Well, why not? Why not? Let me tell you what is coming up. We are going to do an experiment. As you might expect, we're going to throw some metals in water. I know some of you have seen that. And then we're going to throw some more metals into fire, just to see what's going to happen there.
Why not?
Yeah, then we have a special guest who is going to talk to you about radioactive things. He's actually brought some stuff in that's more radioactive than what we have around us. So that's going to be interesting. And then we're going to make some Oobleck and have a quiz to see if anyone can ultimately beat Mr. Morris. What do you think?
It's probably likely I'm going to get beaten.
I think it's very likely. But we'll see. We will see. So would you like to have a look? Any more comments while I go and get ready for the experiment?
Okay, so Mr. Walker is running around the room like crazy to his first experiment, which is the metals in water. So like I said, if you've seen this before, you may have seen it in your science lessons. I'm going to shove over. What have you got over there, Mr. Walker?
We've got all sorts of stuff going on over here.
Things.
Lots of metals. We've got calcium, we've got lithium, we've got sodium, we've got potassium. If you've not seen this before, it is going to be rather good.
Fantastic.
I can tell you now. Any more comments?
No, everyone's just discussing what they've got tomorrow morning, actually. So it looks like Year 7, we've got maths tomorrow morning, period 1.
How exciting.
So we're comparing timetables currently.
I like
very
it.
nice.
I like
no
it.
science questions just yet, but I live in hope.
Very good.
I live in hope.
Very good.
Are we going to you?
I think so.
Let's go to Mr. Walker.
Right. Hello. I can see you through my my special screen here. This is just to protect what's going on, really. We don't want it all over the camera. And when I drop things in, I'm going to do it from the side. So if it bounces backwards, I am safe. But I am going to get some glasses as well. So I'm just popping over. Just going to get myself a nice pair of safety specs on. Safety first. Now, you might think, why am I not wearing gloves? Well, for this experiment, you don't have to wear gloves because it's actually a bit fiddly to hold all the stuff and to move it around. And it's actually safer to do it without gloves as long as you don't touch any of the metals. Now, I have calcium, which we don't normally use, actually. It's not particularly reactive, but I'm just going to put a little blob in just to see what happens. So with calcium, when it touches water, not much happens at all. Let's put a bit more in. More is supposed to happen, but I think it's actually, in fact, if I hold this up to the camera, can you see through there? It's a little bit white, isn't it? It's made a calcium oxide layer. It's oxidized over time, and so I don't think the water is getting through to the metal. Oh, look, the oxide layer was dissolved. Now the water can get to the metal. That is science for you. And we're getting a nice reaction. We're getting hydrogen bubbles coming off the top there. Oh, and now it's fizzing, and the other one is fizzing away. Look at that, perfect. I'm going to put one more in because it's a nice little thing. This is why I don't touch it with my hands, because it would react with the water on my hands, and it would actually burn me. We don't want that, do we? No, we do not. So, that is calcium. The next reactive one we have, sodium, lithium. I do enjoy a little bit of lithium. If you've not seen lithium before, and I think many of you have, it actually floats on the top of the liquid in here, which is oil, not water. It would react with the water. So it looks a little bit like a large pencil, the graphite inside a pencil. And if I hold it with my tweezers and I chop it like this, it's very, very soft. You can't do this with metals, can you? Not normally. I've just cut right the way through, and you might notice that we've got a lovely shiny surface on there. That is actually the metal. This is the lithium oxide on the top. This is the shiny, shiny metal. I can't put a piece in that's that big, so I'm going to chop off a slightly smaller piece, and I'm going to throw that in. I think I can get away with throwing that in. I'm going to move this a little bit further out the way. Let's see what happens with this one. Now, it is a bigger piece, and it is reacting a little bit more vigorously than the calcium did, which I think is quite good. What happens, I hear you ask, if we were to set fire to the hydrogen that is coming off the lithium? Well, we can set fire to it, and in fact, the hydrogen will burn, and the metal itself will burn, and we'll see a colour. So, all the hydrogen is killing me, but that's all right. I'm doing this for you lot. Right, let's put another piece in, and I need a helper. So, I'm going to get Mason, my helper, to come in. Mason is going to light a splint. This is Mason. We knew Leo was coming. Mason's here. What year are you in, Mason? 7. He's in year 7. What form are you in? Hanover, year 7 Hanover. Hooray if anyone else is in year 7 Hanover. Can you light for me, using a match, that splint? Do you think you can do that? Oh, yeah, sure. So I'm going to tap it in. In other words, I'm going to pick up my lithium, I'm going to tap it in, and then, if you light it, I'll take it off you straight away. Here we go. Let's light that splint, and then I can very quickly light the gas, and it will set fire to the metal as well. That's excellent. Thank you very much. That means I can tap it in like that, and I can... Oh, look! We've set fire to the hydrogen, and we've got a red flame, because lithium always gives a red flame when you burn it. Do you want to hold that again? Thank you so much. Let's put another piece in. That was good. Let's do it again. That was exciting. Ready? Let's put this little piece in. You're doing such a good job as my flame holder. Here we go. Oh, that was nice and satisfying. That little hydrogen pop. Wasn't quite a squeaky pop, which is the normal test for hydrogen. One more time. Oh, that lovely red that you always get with lithium. Every metal always gives the same colour when you set it on fire in this way. Well, that was nice, wasn't it? That was good. Shall we do another one, Mason? What do you think? Are you ready? We might need to light the next one, or it might set itself on fire, because it's a little bit more reactive. I know some of you have seen this one. Oh, let's just put the lithium back in there. And we have got... Ooh, sodium. What do you think this looks like, Mason, when it comes out? If I can get this massive piece to come out. What do you think this looks like? Oh, Mr. Humphreys is coming. Come here, Mr. Humphreys. Come here. Come here, Mr. Humphreys. Say hello. You're live on in the lab.
Hello, live in the lab.
There we are. He's just come in. Have you come into...
Welcome to Mr. Walker. He's going to show us an experiment now.
I am. Have you seen this before? This is sodium. We don't touch this with our hands because it's extremely dangerous. What do you think is going to happen when I throw this into water? Bit of steam everywhere. Well, you'll be happy to know we've covered up the smoke alarm, so there's going to be no problem whatever happens. Look at that, nice and safe. So you think we're going to get a nice bit of steam? This is metal. Metal in water normally does nothing, right? Ready? It's that reactive. Look at that, it bounces on the surface of the water and it makes a little ball because it's that reactive. Should we try and set it on fire? Here we go, Mason. Let's get another splint. Here's the big question for you. If we light that, what colour are we going to get? What do you reckon?
Probably blue.
It says blue. It says blue. Any thoughts, Mason? What do you think? See if we can do it before... Quick, before it disappears. Here we go. Otherwise we'll put... Oh, it's going to go. It's all right. We'll put another piece in. Let's put another piece in. Oh, that's a lovely one. Mr. Humphrey says blue. What do you think? Give us a colour. Any colour. Green. It's actually orange. It gives us a nice orange flame. Look at that. It's good, that, isn't it?
Best scientist here, you are, Mr. Walker.
Mr. Morris did not hear that, and he's not giving you the evil eye off camera at all. For that, we can light it again. There we go. Look at that. Oh, I like that. I like that. It's moving so fast, it's blowing itself out sometimes. There we go. Oh, I love that. Well, the last one, I don't think. This looks like a rubber, don't you think? Just a giant eraser. Let's put that back in there. The next one, and incidentally, look, that was a nice shiny surface. It's already reacting with the air in that short amount of time. We don't need to light the next one. I can tell you that now, because the next one is going to do something rather interesting. I thought I'd lost it there. The last one. Let's get a nice decent sized piece out. Oh, this is taking a while, isn't it? This is potassium, and this is my favourite one. While we're doing it, Mason, what colour do you think the flame's going to be on this one? We had red for lithium, orange for sodium. What do you think?
I think it's going to be orange.
You think orange? Orange again? Well, it was red for lithium. It was orange for sodium. Do you think there's going to be a different colour? What do you reckon? Yes, I think there might be. Look at how easy that was to cut through. I'm going to cut through again. It's like so gentle. It's like butter. And we've got the nice shiny surface again. That's your potassium. I'm going to put this size piece in. Let's have a look at what's going to happen this time. Oh, not very much. What happened then? It just decided to sit on the surface. That has never happened before. Let's put another piece in. Oh, surprisingly, not very much at all. Could it be that there is too much oil on it? And actually, we need to wait until the oil disappears. It could be. Oh, look, I saw a little spark there as though the oil was disappearing. And I think it's going to react in a moment. I think it is. In fact, Hannah's going to pass me the blue roll behind her, and we're going to try and absorb the oil on this tiny piece. And maybe, oh, there we go. Once the oil disappears, the potassium starts. Look at that. And off it goes. Oh, I love that. The second one's going to go at some point. Let's have a go with our blue roll. Thank you very much. If I, without touching it with my hands, if I just dab the blue roll on it and take the oil off, always avoiding my skin, we should have more of a reaction. Look at that, a beautiful purple colour. And it got so small, and there was so much heat, it blew itself apart, which I think is absolutely amazing. Oh, I love that experiment. Mr. Morris is going to come in a moment, because he's going to extend this experiment, and he's actually going to set fire to some different metals. Just to show you, these metals over here, if I were to take copper, for example, and I were to put some copper in the water, oh no, nothing happens. Totally unreactive. Nothing happens. But if we add some metals to fire that are less reactive than these ones, we get a slightly different effect. So, Mr. Morris, would you like to have a go?
I certainly would. Could I have some glasses, please, sir?
You certainly can.
Thank you very much. I suppose I should probably put on my snazzy lab coat as well, shouldn't I?
Oh, there you go.
Beautiful. So, very simply put, when metals, or any atoms that matter, get heated up, the electrons in their structure get really excited, and they will go to different energy levels. They go to higher energy levels. And then as those electrons come back down again, Mr. Walker's potassium has just gone off over there, I can see. As the electrons come back down again from that high energy level, they will release the energy at specific wavelengths. In other words, they will give off different colours of light. So we've got three metals here. I've got some iron filings, I've got some copper powder, and I've got some magnesium powder. And I've also got a nice little spray here. I think Mr. Walker's going to let me use that. Fantastic. So could I have some splints, please, sir? Thank you very much. And would one of you guys like to just flick the lights down for me so I can show this off? Thank you very much. Fantastic. There we go. Now, some of these colours you'll recognise from fireworks. So when it's that time of the year and there's fireworks going off, and you might see different colours in the sky, red, orange, yellow, blue, green. Those colours are all produced by the heating of metals, because those electrons get excited, they come back down, and they will release different wavelengths of light. So if I put copper in a flame, we get this fantastic green colour. Now, sometimes you might use a Bunsen burner in science and go, oh, the flame's green, why is the flame green? Well, the flame's probably green because someone before you has been using copper metal in their flame test, just like this. Because actually, we can use this idea to test for different metals in different substances. So if you were to be interested, if you're interested in analytical chemistry, you want to go and work in a lab, you would use something called flame emission spectroscopy, where you would use this idea that certain metals will give off certain wavelengths of light. And depending on how strong they are, depends on how much you've got. So copper we saw was a nice green colour. We've also got some iron filings. And all I'm doing, a little dab of water just to make the metal stick. And then our iron filings, you can see. Now, what does that remind you of? What does that remind you of, guys?
Fireworks.
Fireworks, yeah, sparklers, exactly, thank you. So, sparklers, they're just made of iron filings. And when we heat them up, they get nice and hot. They will give off this lovely sparkler effect as they oxidize. It's much better than just plain old rust. And then lastly, we've got some magnesium powder. Now, if you've seen magnesium powder burn before, or you've seen magnesium burn before, just pop a comment for me in the chat and just tell me what you normally would see. Maybe you have, maybe you haven't, doesn't matter either way. But just tell me what you might expect to see. And we'll see if you are correct. So magnesium, very reactive, burns.
Oh, it's good that.
Much like a sparkler, but much brighter than the iron. I'm going to use that one again because that was my favourite, even though I probably should have looked away because my eyes are now a little bit...
a bit dazzled.
I'm a bit blinky,
yeah.
a bit dazzled now. There we go. Beautiful, fantastic. So those electrons getting really excited and emitting those different wavelengths of light.
That's good, isn't it?
Absolutely fantastic. Now we can also dissolve metals or add metals to a solution or another liquid. This is ethanol, if I'm correct, sir.
It is indeed.
It is a bit of ethanol. So a little bit of alcohol, a bit of flammable alcohol. And sir's very kindly popped some copper powder in there for us. We know copper burns green, but we can spray it into the flame and we should see a nice green colour.
Shake it up a bit.
Appearing.
Are we getting it?
As the spray, hang on, let's give it a second, there we go.
Oh.
As the ethanol burns in the spray. Oh, I've blown it out.
We've lost it.
I've blown it out. Never mind. Let's see if we can relight it without setting myself on fire. There we go.
Well done.
So you can just see a little bit of green showing there.
It's not as green as normal, to be
Not
honest.
as green as normal.
A little bit,
There's
just
a
a
little
fraction.
bit there.
Oh, a bit,
fraction of
yeah.
green. There we go.
Do you know what? While you're there,
While I'm here,
I'm going to get some magnesium.
are you
powder.
doing some? Are you going to
Yeah.
do your famous sprinkly
Yeah.
magnesium?
I mean, this is
I
how-
like the copper.
That's cool,
personally.
isn't it? That's how you're supposed
That's
to do
my
it.
favourite.
But I kind of like to do it like this. Oh, just throw a little bit in. As long as I throw in from the side,
Like you're a wizard, sir.
like I'm a wizard, like I'm going Expelliarmus. Oh, that's quite good. Oh, I can't think of any other spells, so that's why I went. Oh.
Other wizard franchises are available.
That is quite good, isn't it? You ready? Oh,
Oh,
let's do the biggest amount. Ready? Oh, that wasn't actually that big. Look at that. It's great, isn't it? Oh, and
Oh,
it's gone
you
out
blew
again.
it out.
Well, that was an appropriate time to finish that, wasn't it? I'll head back and see if we've got any questions. Oh, well, that was good. I hope you enjoyed that, everybody. That was a lot of fun. And here we are. The lights are coming back on. And, oh, yes, I'm still having a look over there. Are we back onto me? Oh, yes. Yes, there we go. Right, let's take the glasses off and see if we have any comments. We have got plenty of stuff going on there.
I've got loads.
Oh,
Flames.
We have, haven't we? Flames.
Sparks. This must have been in answer to my magnesium question. How does the fire and magnesium make a weird colour? What do you mean, Hamish? What do you mean by a weird colour? Like that bright white colour?
Yeah, maybe so. A really bright, white, sparkly colour. Why does it do that?
Well, it's a very exothermic reaction, isn't it? When it reacts with the oxygen in the air and it burns.
Yeah.
It also has the electrons getting excited and coming back down to release the energy.
Mm-hmm. And it's more reactive, isn't it? On the reactivity
It is
scale,
more reactive.
it's higher up. Not as high as lithium, sodium, potassium, which reacts with water. But if we put a bit of energy into the metals, we get a lot of energy out, like magnesium. And then as it goes down, copper, and then we've got
Less and
iron
less
and things
reactive.
like that, if I've got that right. So yeah, any other questions you can ask us. You've got about a minute or so before we go over to our special guest, who I don't think any of you have ever met before, but you might see him around school. He does work for the Great Schools Trust, so he is sometimes working. If you see him, say hi. I'm sure he will love the fact that you know that he was in the video. So just say to him, I saw you in the lab live, and do say hello to him in a moment. When is your next live? The question has popped up. Now. Now is the next live. Hopefully we'll do another one in May, in the May half term, and that'll take us up to summer. So one more, I think, probably before the summer holidays. But I do have to say we've got another special guest who I almost forgot. I'm very sorry, I almost forgot him. It's terrible. We need to see what Albert Speinstein has to say about the previous experiment. So let's have a look at what he has to say. Here we go now. Well, yes, he's looking very happy as normal. He's looking a little bit more healthy, I think, than he normally does. A little bit more meat on his bones, to be honest with you. But
I think that's subjective.
Yeah, that is true. I'm sure he'll change a little bit more through the rest of the time we've got. So I will head over to our guest if you want to have a look at any more questions for a moment, and you could join me as well if you wish. Oh, I'm coming.
So I've got some exciting stuff to show you, Mr. Walker.
Do you know what? We haven't introduced you yet. We haven't introduced you. So this is Stephen Thornley. Stephen, that's right, isn't it? I keep getting his name wrong. Stephen Thornley. So you can say hi, sir, if you see him in the corridors. But for now, we're allowed to call him Stephen. So you work for the Great Schools Trust, don't you? Just tell us what your job is.
I'm in charge of all the data in all the schools. So anything data-wise, that's me.
That is. And remember, if you see him, do say hi. Say, I saw you in the video.
I'm usually wearing some silly earring.
So there you go. There you go.
What I've got on that day.
Now go for it. Tell us, what have you got? Because this is different.
I've got some really exciting things. So this, to start with, is called a Geiger counter. And what this does is counts how much radiation there is. And the way this works is here, there is a tube that's filled with noble gas, mainly argon or helium. And what happens is when radiation hits, it ionizes one of those particles, and that creates a charge, which is then counted by this little box.
All right. Okay.
So what you can hear now is clicking. I think you might just be able to hear it.
Yeah.
And that's the radiation that's just naturally occurring in everyday life.
So it's only there every so often, every couple of seconds or so. Very low radiation. That's right, isn't it?
Yep, indeed.
Okay. Right.
Low level radiation.
Nice.
But we've also got this. Now this is uranium glass, which
Ooh.
is basically just a bit of glass
Woohoo.
that has uranium in it. It's encapsulated, and it makes pretty glass. So, as you'd expect, uranium is radioactive.
Yeah.
But glass works really well at stopping that radiation, and that's why they use it to store high-level nuclear waste.
Right. So we know the background radiation.
Yeah, we know the background radiation.
And this should change.
Right.
You think it's going to change?
And it should go up, but not by a lot. So you can hear it clicking more.
Yeah, that is noticeably more, isn't it? A few more. Oh. There we go. A few more clicks there.
And the radiation we're measuring there is the uranium breaks down because it's a really big atom.
Yeah.
And it turns into radium. And radium emits gamma radiation. So that is what we're picking up because that can get out of the glass because that's just an electromagnetic wave. Whereas the other radiation that normally comes out of uranium, so alpha particles, which are helium nucleuses, and beta particles, they get trapped in the glass.
Right.
And you can measure the age of this glass if you know what the uranium was content when you put it in. And you can measure how much lead there is because eventually it breaks down into lead. And that'll tell you how long ago this glass was made.
I see. So every time you hear a little click, that's radiation coming out of the glass. Or it's radiation coming out of space or the Earth or us, and that's what this is picking up. These little bits of radiation, and of course there's more here. So how come this is safe? Because when we hear of uranium, we think of, those glowing green bars from The Simpsons and things like that. So how come I can hold this and I'm not dead?
So basically, a lot of radiation is quite big, quite bulky, and not very good at going very far.
Yeah.
So that's alpha particles and beta particles. And usually what you use to stop those, you can use paper to stop alpha particles, you can use a thin layer of aluminium to stop beta particles. So the only thing that gets out is that bit of gamma radiation.
And a tiny bit is okay.
And a tiny bit.
Tiny bit. So if we had the uranium from here and it wasn't in the glass, it was just in a lump, that would be much more dangerous because we haven't got the glass to stop the alpha and beta. Right. Okay. So actually, it is quite dangerous, but we've made it not dangerous. We've made it safe. And people have these in their homes, don't they? Doesn't mean that all green glass has uranium in, so don't think that, by the way, because you can just get normal green glass. But special uranium glass. Wow. And even if we smashed it, the uranium wouldn't get out, would it?
No, I wouldn't breathe it in, but
Yeah.
yeah, it's
So,
safe.
okay, so all the bits would have it in, but it's safe. All right, okay. Go on.
No, okay. Another really fun thing about uranium glass is it's called something called fluorescence, and that leads on from kind of what we've been doing with the flames.
Yes.
That there's other ways to excite electrons, not just with heat, not just with energy, and not just with water with the group 1 metals.
I like it, I like it.
So if you could turn the lights out, please.
Oh, here we go. Our helpers are getting to the lights. Leo got there first. Here we go.
So if you use a UV torch, you can make it fluoresce. It glows. And exactly the same as the
It does.
metals. It excites the electrons to a higher energy level. They then drop back down and emit this glowing light you see.
So it's that dropping down that just makes the light go, come out.
It's the photon and away it
Interesting.
goes.
All right, okay. Look at that. It does actually fluoresce, doesn't it? It's definitely brighter.
Really pretty. For context,
Yeah.
this is just shining UV light on normal glass.
Yeah.
Not much happens.
Yeah.
Not at all.
Just, slightly violety, that's all. But that's more blue and green. Yeah.
But you do get fluorescent in everyday objects too.
Oh, yeah.
So if we look here, we've got some tonic water, we've got some lemonade, and we've just got some normal tap water. Which one of these do you think is going to fluoresce?
Right. Comments. Mr. Morris is watching the comments.
I am
Let's
watching
see
the comments.
what you think. Which one is going to fluoresce more? Anyone give us a comment? Let's see. Let's see.
I feel like I need like a little countdown
Go
timer
for
of
it.
some
While you're doing
description.
that, while we're waiting for comments, actually, do you know we've got a couple of items over there? I don't know if you've heard this before, but they do say that bananas have got a slightly higher radioactive count than most other things around us. And Brazil nuts, slightly higher as well. And that's just to do with the chemical composition that's in there and the amount of radioactive isotopes that you find in those particular things. But it's not dangerous levels, because we eat bananas all the time, don't we? You'd have to eat tons and tons of bananas to have the same effect as, say, an X-ray, wouldn't you? So it's not going to be a problem. But we just want to see if we can get a difference. So let's just listen quietly while you're commenting on the liquids. Ooh, I don't know, possibly.
Should we try the Brazil?
Yeah, Brazil nuts are supposed to be slightly more. Here we go. Well, these Brazil nuts are totally all right. I mean, to be honest, I did buy them from Asda probably a couple of years ago, and they've been in the cupboard. So maybe all the radiation has already left, because over time it does leave, and then it becomes safer over time, doesn't it? So that may well have happened, to be honest with you. Any comments, Mr. Morris?
We've got a few votes.
Right.
We've got a few votes for tonic water.
So you think tonic water fluorescing more?
Yes.
All right.
We've also got a few votes just for the glass beakers themselves, fluorescing quite a lot.
Okay. Just the
But
glass.
no votes for lemonade and no votes for water.
For water.
Oh, there is a question here for you, Mr. Thornley. It says, what is your favourite element in the periodic table?
My favourite element, and the best element,
Uranium.
far and away, is boron.
Oh,
But it's boring.
boring. That's what I always say. That.
It's objectively true, boron is the best.
There you go.
And it's actually used in nuclear reactors to stop radioactivity.
Actually, that is important, isn't it?
In a uranium, you have in a nuclear reactor, you have control rods, and they're made out of boron. And you put those in when you want the reaction to stop. And if they've done that correctly at Chernobyl, then lots of bad things wouldn't have happened.
So all these places like Fukushima and places like that where everything went wrong, it's those putting in the boron rods, something went wrong in that process, and it just escalated and escalated. Well, we need to find out about fluorescing.
A few more questions actually before you do.
Oh, go on, let's do it.
Everyone
Let's do
is
the
very
questions.
interested in
Here we
this
go.
banana.
Questions. All right.
So there's lots of questions about the potassium in the banana. And
Yes.
Does it affect the radiation?
So the radiation
Yeah.
in the banana comes from the potassium. So there is a isotope of potassium that is radioactive, and that's actually what they use. If you've heard of carbon dating, there's also potassium dating, and that's what's measured, the reactivity of the potassium within a structure to see how old it is.
And you might be thinking, hang on, Mr. Walker threw some potassium into water earlier on. Follow me. Come over here. Watch, because we've still got the water over here. So there's potassium in a banana. Oh, explodes. No, it doesn't. Because it's not potassium metal, it's potassium compounds. the potassium's reacted with other things. It might be, I don't know, I'm just making it up, potassium chloride, potassium bromide, might be all sorts of stuff like that. So it's not actually potassium metal. That's why it didn't explode and cause a big problem. So you can eat potassium compounds, but not potassium metal. So, any more questions, sir, or are we going back over here?
No, just a couple of votes for lemonade, but overwhelmingly
lemonade
for this tonic water.
Right,
so.
over to you.
Let's go. Let's start with water. Nope, not really doing anything. Then do lemonade again, and we already know the answer.
Yeah.
It's already fluorescent.
Yeah, look at that.
And then tonic water.
That's cool.
So there's a compound in tonic water
Look at that.
called quinine, and that fluoresces. And quinine is actually a medication used to treat malaria. And that's why it was put in tonic water for rich white people in Africa,
Oh, right.
in West Africa.
Look at that. Look at that. So you're actually giving yourself a minor bit of protection when you have tonic water, just in case we come across malaria. Just a tiny little bit of protection. Is that right?
Yes, we are.
You used to put it in Tizer as well, if anybody remembers Tizer. If anyone old is watching like me, that fizzy drink Tizer had quinine in as well. That is very good. Have you got anything else there to show us?
Last but not least, fluorescence is used in everyday life for certain aspects, and one of the things it's used for is in laundry powder and laundry detergent. It's basically, what it does is it just makes your whites whiter. I'm not quoting anything there. But this is really exciting to see, because if you've got some laundry powder at home and you've got access to a UV touch, you can see this, and it fluoresces really pretty, really blue. Okay. Right, thanks guys. Back to you, Mr. Warren.
Thank you very much.
Any more questions?
No questions, but a lot of love for the fluorescence.
Oh,
There's a lot of
it's
wows
good.
in this conversation.
It's
the
very good,
fluorescence.
isn't it?
There's a few saying you're my favourite. I wish you could be my teacher. So thanks. Cheers. Me and Mr. Walker. Must be, yeah, chopped liver. Thank you very much. So, a couple of questions. Would pure lemon juice do the same as lemonade when it comes to fluorescing?
So it doesn't fluoresce. Lemon juice doesn't fluoresce because the stuff that's in the water that potentially fluoresces is basically citric acid, sugar, and water. That's basically what lemonade is. That's more or less exactly what's in lemons, but more concentrated. So no, lemon juice wouldn't fluoresce.
Thank you very much. Let's see if Mr. Feinstein has any thoughts on that.
God, typical. Nothing.
No, been too busy getting changed.
Useless. Oh, well, never mind.
Terrible. Can't get the staff. So, we are going to go over now to our helpers. They're at the back there. They're ready to go. Mr. Walker, are you joining in, sir? Are you
Yes,
competing
indeed.
in this?
We are. This is not a competition bit. This is a fun bit before the quiz. The quiz is coming.
Oh,
So,
I'm the only one competing. Okay, that's
it's just
fine.
you. We just want to beat you. This was these guys' idea. They want to beat you. So there we go. Okay. Are we ready?
We are going to go over to Mr. Walker, and he's
Indeed.
going to make us some oobleck.
That is correct. That is correct. Stephen, would you like to join in as well?
Yes,
Yeah, we want to get him involved. We do. In fact, Isaac can get involved. Do we want Isaac involved in it as well? Wave to the camera anyway. Come and give us a wave. Give us a wave. Oh, typical tech person. Right, so Oobleck. What is Oobleck? Do you know? Tell us. You know, Leo.
Like slime. It was with literally liquid, but then it turned into a solid like so.
You've got it. It's a bit like slime, isn't it, to start with? And it's a liquid that can turn into a solid. And you might be thinking, if you've not seen this before, what on earth are we talking about? So we have got corn flour here that you can buy from a shop. We've got an evaporating dish. You can use any kind of container. I just like these. I'm going to give one of these to each of these guys, and they are going to add some corn flour in, and then they're going to add some water from the sinks behind me, and they're going to try and make Oobleck. If they get the ratio right, that means the amount of water to the amount of corn flour correct, they will have made perfect Oobleck. And that means it will be runny when they move it slowly, and it will go firm as soon as they add pressure to it. So let's see if we can do that. So guys, would you like to grab yourself some corn flour, one of these dishes, and we'll see what we come up with. I might give it a go as well. So Hannah, you can start by pouring in what you think is the right amount into there. Tell us in the comments who you think is going to make the best Oobleck. Could be anyone here. I will tell you that these guys had a little practice yesterday. Stephen didn't. Might affect your results. It might do, it might not. I don't know. Has he got inherent Oobleck genius? We will find out. So whenever you want, head over to the sinks, guys. Add in a certain amount of water. You might want to add in a lot. Or you might want to add in a little bit and then keep adding a bit in and mixing it in. It's totally up to you what technique you do. I'm going to have a go. Doesn't mean I'm going to get it right because I normally measure it out. And I have written down the perfect ratio somewhere, and I'm not following it today. So let's have a look at what you've got. Right, you need to push it in, don't you? Mix it in, mix it in. Let's have a go there. All right, interesting.
That's a bit too much.
It's a little bit too much. You want to hold it up to the camera there. Hold it a little bit closer. A bit too much what?
Corn flour.
Too much corn flour. So what could we do? A bit more water. That's it. That's how it works, really. Keep adding a little bit of what you think you need. We're going to come right up to the camera and show you in a moment. Go around there and show the camera what you have made. Go right up and show. Yeah, it's a little bit liquidy, isn't it, really? It's a little bit liquidy. Right, Isaac's coming around with the camera and he's going to see different people and see what you've done. Yours is a bit like soup at the moment, Mason. That's interesting there. Interesting. It's gone a little bit quiet in the other part of the room over here. Not sure what. Let's have a look over here. Anything good? It's a bit liquidy, isn't it? Mine's a bit too liquidy. We've all gone too liquidy. Mason, I think, has done it. Okay, so tip it, see what happens. Tip it. Look at that's quite liquidy. And then when you hit it, and then just to prove it, sink your finger in slowly, just to show. See, it is actually liquid when you do it gently. But as soon as you put pressure onto it, the molecules change their alignment and they become a solid. You've done it. He's actually done it. If you said Mason in the comments, you would be correct. He did it first. Any comments?
Well done, Jamie. Whoever Jamie is, he said Mason.
Well, he did it. I'm going to have to add a lot more into mine to get any sort of progress. Do you want to add some more? You can add. Well, we will do that in a little bit. We're going to extend the experiment in a few moments' time. So what we're going to do is, this quiz that we were talking about, we're going to have a quiz to finish off today. And while we do a quiz, no, I've not made it. Not successful. While we do a quiz, Mason and Stephen, if he wants to, can even continue to the side because we have got some extra ingredients. We have got some oil. We have got some baking powder. We have got some proper starch that you kind of get from potatoes. Some petroleum jelly. And a few different colours, as well as some toothpaste. Now, maybe this will improve the Oobleck. Maybe we'll make a whole new substance and we can name it, and it'll be far more exciting than anything we've ever seen before. Or it'll be a mess. We will see what is going to happen. So I'm going to move this. I forgot to say, we've also got salt and sugar for a bit of texture. So I'm going to move this a little bit off to the side, and Stephen and Mason are going to experiment, and they'll show us at the end what they have experimented. So I'm just going to move this over here. So guys, you can come over to this bit. Mason, take your stuff over there. Because we are very, very soon going to have a quiz. So are we ready? Are we ready to go to our little quiz section? All right, we're nearly ready for the quiz section. Isaac's just getting himself sorted while I tidy up our little section here. How did you do, Stephen, with your Oobleck?
Not well.
No, you've thrown it away. You've not even.
thrown it on myself.
Yeah, it does kind of get everywhere, but I like gardening, I like mess. That is pretty much as it is. While we are waiting, I'll just show you mine, and if you can see that, it's far too liquidy. There's a sense of Oobleck to it. Do you know, there's a kind of Ooblecky feel to it, but it's not perfect, if I'm honest. This is Hannah's. Hannah's just given me this, and she thinks she's got it spot on. It moves around. Oh, yes! And I hit it. Look at that. Tap that. Absolutely solid, isn't it, when we tap it?
And do you know what that's called?
Oh, yes, I didn't mention it. Go on, tell us.
It's called a non-Newtonian fluid.
Absolutely. And it can go both ways, can't it? It could start off a solid and become a liquid, or it could start off a liquid like this and become a solid when you put pressure in, depending what the substance is. Different things do different things. Now, if I've got it right, ketchup is normally quite solid until you shake it, and then it becomes more of a liquid. That's why we shake it, to get it out. Quicksand, that's a solid till we put pressure on it, and that becomes a liquid. Corn flour is a liquid when you've added water until you add pressure, and then, of course, it becomes nice and solid. So, yeah, it works a little bit both ways. Why is it called non-Newtonian?
Because it doesn't behave like you expect it to. Like it's within the Newtonian laws of physics.
So So Isaac Newton, I guess, he was the one who said this is how things behave, and it doesn't follow that pattern of solid, liquid, etc. Right, so are we just about ready? Isaac is going to start off. I believe we have a little intro, so here we go for the quiz. Now the quiz should be just about ready. Are we there, Isaac? We are there. And here I am, the quiz master of the ultimate quiz. So can we have our first contestant, please, who is Leo? Here you are, here you are. And I do have a couple of special buzzers that we are going to use for this quiz. And a couple of different things that might make it a little bit more interesting. Leo is actually going to, first of all, go against Hannah. So Hannah's here, and the winner will then go against Mr. Morris. So we have a younger contestant, an older contestant, and then, of course, a very experienced contestant. So we shall see who is going to win there. Mr. Morris, could you grab my piece of paper without looking at anything on that paper? Showing, oh no, he's decided to let Stephen do it because he can't be trusted to do it. I totally get that, that's fine. So my piece of paper with the questions is coming this way. Thank you very much. The questions have all been pre-recorded. So myself and Isaac went round school, we recorded them in different places, just to make it a little bit more interesting. So, first of all, we're going to ask 3 questions between you. So, a question for you, then for you, back and forth. The winner will take on Mr. Morris. So, first question, Isaac. Octopus have?
That is very wrong.
That's what I hit if you get the answer wrong. That is not for you to hit. So, that is the wrong one, and...
Correct.
Can you tell me who recorded that earlier on? I'll do it again if you get it wrong.
That is very wrong.
Whose voice is that?
Correct.
Who is that? Anybody know who that is? Go on, Mason. It wasn't Isaac. And she will not be happy to hear that you said Isaac. It was, in fact...
That is very wrong.
Miss Ashley. She provided the voices for our buzzers earlier on, but thank you for giving it a go. It is your question. So you were so keen to get in there. What's the answer?
3 hearts.
Correct.
So 1 point to Leo. Okay, question 2. Here we go, Isaac. Oh, the question seems to have stalled a little bit. Oh, the question stalled. Here we go. Can we see it? Otherwise, I can read it, which is totally fine. What do you think, Isaac? Oh. What's the difference between mass... Oh, that was a good question. Mass, I'll read it out on here. What's the difference between, this is for you, between mass and weight? Mass is like the...
That is very wrong.
That is wrong. Do you know what mass and weight is? Can you help there? It's not a trick question, because mass is the amount of stuff that you have, the number of particles that you have, the amount of stuff. Whereas weight is the force downwards due to gravity. There you go. So that means 1-0 so far. How's the next question going? Let's see if we can do it. Otherwise, I will read it out, Isaac. Here we go. Oh, nearly. We gave it a go. Do you know what? I'll just read them out. That's okay. You like it when things go wrong, don't you, people at home? Absolutely. Okay, so question for Leo. What is the difference between a vertebrate and an invertebrate?
An invertebrate doesn't have a backbone, but
An invertebrate has no backbone. A vertebrate does.
Correct.
Very good. 2-0 so far. Oh dear, Hannah, this bodes well for GCSEs. Okay, next question. What is the process, Hannah, that plants use to make food? What do you think?
make food.
I can tell you it was.
Correct.
It is actually correct. That is the process for making food. You might have been thinking of respiration, which is the opposite process. And I can see it's easy to get that confused. So that means 2-1 over there. Okay, don't look at my sheet. I saw that. The next question is for you. Third question. At what temperature does water boil at, Leo? 100 degrees. What's yes! That is it. So we're on 3-1. So whatever happens, Hannah's lost. Right, last question. Last question. I can't even find where the question is. Oh, there it is. Let's give her a slightly easy one. We've been talking about Oobleck. What are the states of matter? Solid, liquid, and gas. Are we going to let her have that, Mr. Morris, or should we push her for an even fuller answer? What do you think? What do you think he's thinking? He's thinking. Can you expand? Because there technically is a fourth state of matter, actually. No, steam would be... No, you're thinking about names for certain types of water in states of matter there. Anybody know? We've got... I'm still going to give you... Because you were correct. But there is a fourth one. Anybody know? We've got solid, liquid, gas. Plasma. Look that up if you're interested in finding out more about plasma. So the score there is 3 to Leo, 2 to Hannah. That didn't work. Tell you what, let's turn that one on. Yes, well done to you. So Hannah, off you go. You are away. You are away. Okay, we're going to have Mr. Morris come now. Here we go for Mr. Morris. Here he is. Yes. He's on the stage. He's on the stage. Do you think you're going to win? We will see. We will see if that is true or not. I enjoy this far too much. I think Isaac thinks he has the questions back again. So I think we're going to ask question number 7 now to Leo. Best of 3. Okay, so question 7. Leo, here is your question. What organ of the body is used for processing thoughts and information from the nervous system? Aspire. Okay, so did you get that? Go on, it's easy. It is the brain. So 1 point there. Do you want to try the next question? Here we go. Mr. Morris's question. To the closest billion, how many nerves are in the human brain? Okay, so the closest billion, how many nerves are in the human brain? Let's see, let's see. What is the answer?
90.
That is very wrong.
Miss Ashley is disappointed because the answer is 86.
It wasn't that wrong.
It wasn't that wrong. Yeah, it wasn't that wrong, Miss Ashley. It was just a bit wrong, not very wrong. But not quite. So 1-0, 1-0. Next question for Leo. What is the closest planet to the sun? Oh, closest to the sun. Is it Mercury? Is it Mercury? That is correct. Very good. So 2-0 so far. Here's Mr. Morris's question. To the closest sextillion, how many stars do scientists think there are in the universe? Oh, now that's an easy one for Mr. Morris. Let's see if he can remember the answer. Closest sextillion. Remember, there's billion, trillion, quadrillion, quintillion, sextillion. That is a lot. He's thinking. He's thinking. The answer is
200.
He has said 200, and the answer. He's actually got it spot on, according to the sources we looked at.
Get him.
200 sextillion. I'm going to cover up the last answer.
Thank you, Instagram.
Is that what it was? So we have got 2-1, 2-1. Another question, last question for Leo. Here we go. Can you give me 3 examples of sea creatures that are not fish? All right, over to you, Leo. 3. This is hard.
Whale.
Yes, because that is a mammal.
Dolphin.
A dolphin is a mammal as well, so that is not a fish. What else could we say?
A shark.
Oh, I think a shark comes under fish. I'll give you another try. something else that's not, anything in the sea that's living but not a fish. What do you think? What do you think?
Crab.
He's saying a crab.
Well done.
Yes, very good, very good. That is 3 points. Okay, let's see what happens on our final question. Here we go. To the closest Mr. Morris. How many Mr. Morrises deep is the deepest part of the ocean? Of the sea was going to be the rest of that question. So, how many Mr. Morrises deep is the deepest part of the sea? Now, you should know because that is you. That is your height. We worked it out very carefully. So, how many Mr. Morrises deep? What do you think? What do you think? I need an exact answer. What do you reckon? What are you going to go for?
10,000? I don't know.
Oh, that really is. That is very, very, very wrong. I hope you could hear that in case you couldn't.
That is very wrong.
That's what we've been hearing from Miss Ashley.
It was very wrong.
It was very wrong because the answer obviously is 6,127.1 Mr. Morrises. That is 10,894 metres deep, which is very, very deep, over 10 kilometres deep. So that's the Mariana Trench. So that means that the total score was 3 points to 1.
Well done, Leo.
Yes. All this cheering just for you. Everyone's cheering at home. I'll let you go back over there, Mr. Morris.
Thank you very much.
In disgrace.
In disgrace, yeah.
To read the final comments while we finish. So I do hope that you enjoyed it. Thank you very much, everyone. Very fun. So back to Mr. Morris in the studio.
Well, Miss Salt's been on to the chat and she's been answering a couple of questions while we've been busy quizzing.
Yeah.
So thank you very much, Miss Salt. We had a question for you, Mr. Walker, which was why iron has the symbol Fe and not IR. But Miss Salt expertly answered it. So the symbol Fe represents the chemical element iron.
Yes.
The symbol is derived from the Latin word ferrum, which means iron.
I do
Thank you
like
very
that.
much, Miss Salt.
And you always find that. You always
Miss
get...
Salt just volunteered to be your special guest next time.
Oh, next after May in the lab
Yeah.
live 3. We've all seen it, haven't we? That Miss Salt said yes, she would do
we all
it.
saw that.
We like that.
As soon as she got engaged, that was it. Thank you, Miss Salt. We appreciate that.
I will add to that though that there are lots of other elements, and you might look at the symbols and say, why is that symbol not as I would expect it to be? We've got all sorts of weird ones like tungsten, which is W. And that comes from wolfram, the old name for tungsten. What else have we got? We've got HG.
AU.
AG.
There's
all sorts of them. Yeah, W.
Oh,
we did,
W.
but that's
Sorry,
all right.
I was reading.
I'll tell you the story for HG.
NA.
NA, I like that one. I like that one. And they all come from old names usually. HG, I believe, means hydrogyrum, which means quicksilver, because mercury looks like silver moving very quickly. It's a good one, isn't it, that one?
My favourite one is the one you tell about magnesium and manganese. MG
Oh, yeah, that's good. That's good. Did you want me to tell it?
Of course, please.
Magnesia is a place in Greece, and they were both discovered or linked to finding a lot of those two elements in magnesia. So if you ever go to magnesia, you can say, the home of manganese and magnesium. Or you've got the bismuth there, look.
I have got the bismuth.
It's nice, isn't it? I like that.
It's very shiny.
Yeah.
Nice crystal structure. Have you melted this down and done it again?
No,
or is it broken?
it just keeps breaking bits off there. Yeah. But if you want to have a look at that at some point, you can come and knock on my door because it lives in my prep room and you can see it's really, really nice. Everybody likes it. But I'm going to take it off you because it's actually none of your bismuth. Carry on. Any other questions?
Oh, dear me.
Yeah.
What is your favourite element, Mr. Walker?
This one, because it looks so cool. Genuinely, look at it. You can melt it, and then when you kind of solidify it back again, I think it was actually solidified like that, and you knock the film off, and you find all these wonderful different shapes have formed. That's the oxide layer on the top, actually, and it's all about how the light refracts off it because of the thickness of the layer that gives the different colours. Really quite nice.
Very beautiful.
So there you go.
Are there any elements which aren't in the periodic table?
No. If it's an element, it's in the periodic table. There might be elements we've not discovered yet, or created, we should say, because the higher ones, the ones with bigger weight or bigger mass, we are putting them together and they fall apart quickly. So we might manage to do that with other things, but if it's an element, well, it's in the periodic table, isn't it?
Yeah. Someone spotted that copper has the symbol Cu.
Oh, absolutely.
And has asked, where is the word for copper from? So the Cu is cupric, isn't it?
It is, or cuprum, I think, originally,
Cuprum.
because it comes from the old word for Cyprus. Because, again, it's got a
Lots of
link
copper
to
in
Cyprus.
Very
and
nice.
that's where it comes from.
Very nice.
Any more questions? I mean, we could have other people answering them. Go on then. Yeah. Let's get anyone else.
You've already answered, Stephen, what your favourite element is.
He has. He has.
Boron.
Have we got there? I think we've just about got there. We've got to the end. And look at the time now. We have nearly been live for about an hour. If you include the pre-little bit screen that we watched, then it's over now. So maybe it's time to say goodbye and wrap it up for another session. Until In the Lab Live 3 with Ms. Salt. Ha 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 ha. Okay. Thank you very much for watching. You can watch any bits that you've missed. You can send us some messages if you want to be involved in anything like the guys did. Then, of course, you can do that. And we have forgotten one thing. Two things, in fact, that we've got to fit in. Mason has been busy working away on his creations. So bring your stuff over here, Mason. Bring us what you've created and we'll show the new, improved Oobleck just before we finish. Because we nearly finished.
Excited or nervous about this Oobleck?
Take it right up to the camera there.
I don't know.
You don't know?
No.
What's in it?
Dye, toothpaste, and dye.
And
It mostly looks like I've been bleeding into it. But
has it got any interesting properties?
it
smells
like
very
a
minty.
It smells like a dentist's office.
Oh, it does. It's nicer to smell than Oobleck. What happens if you tap it? It goes all over Mr. Morris's shirt. That's what happens. It's interesting. Doesn't go firm, does it? You get to mix in the colour. Yeah, I like that. Well, very nice, very nice. Absolutely. So, I think with that then, unless we have any more comments, no, we've just got nice
a vote for Miss Taylor next time as well as your helper.
Was that from Miss Salt saying it should be Miss Taylor? Just wondering.
Absolutely, yeah, that was from Miss Salt. Miss Salt said Miss Taylor would much prefer to do that.
Maybe we'll get everyone.
We'll just have to argue about it, won't we? They'll have to fight amongst themselves.
To see who gets the pleasure of our company. Well, thank you very much for watching. Thank you to all our helpers, to Isaac, who has been running the cameras, to Hannah, who's been been very helpful all the time, to Leo, to Mason, thank you to Stephen, Mr. Morris, and thank you to Albert Speinstein as well.
And Mr. Walker.
Thank you very much.
For organising everything.
So, see you next time. Bye, everyone.
Bye.